So following on with additional proposed methods to decompose a signal using dictionaries, we have the best orthogonal basis, BOB method. As we mentioned earlier, a dictionary is a collection of parameterized waveforms. D equals phi gamma, where gamma is the parameter and it belongs to a specific set. The goal here is always to find the vector of coefficients alpha such that the signal S is equal to phi, the matrix of atoms, times alpha. However, with the best orthogonal basis, so the BOB algorithm, we take a very different approach. Instead of building up a sequence of sparse approximations of S, like in the matching pursuit algorithm, the best orthogonal basis algorithm begins by taking advantage of the special structure of some dictionaries, like wavelets or cosine packets. As it turns out, it is shockingly possible within these dictionaries to identify many subcollections of atoms that form orthogonal bases. The way I interpret this is in terms of an abstract vector space, where we define the quote unquote vectors as the functions within the dictionary, and we see that they are supposedly orthogonal under some definition of inner product, which doesn't necessarily match the dot product. Anyway, so once the subcollections are cut out, the best bases can be chosen by means of a custom defined entropy transformation, I think. Essentially, you take the vector of coefficients of S in an orthogonal basis, like a coordinate vector. You apply an undisclosed scalar function E to each of the components, and then I think you just add up all the elements to obtain the entropy associated with that basis. Once you have the entropy value, you do the same for all the subcollections, and you just keep the basis with the lowest entropy. My interpretation is that once you have the orthogonal basis, the system S equals phi alpha becomes very simple to solve, as the inverse can be easily found as phi transpose times S equals alpha. So this method is supposedly pretty fast, in the order of n log n, and it typically delivers solutions that are as sparse as possible. However, it can fail when the signal is made of very few highly non-orthogonal components. For example, the Werner-Soros curve, which is in one of the documents. The other method, which we already discussed in previous presentations, is the basis pursuit method. The difference I see is that while the best orthogonal basis directly provides a unique answer by cutting all the dictionary items that do not fall in the chosen subcollection, the BP, the basis pursuit method, deals with the overcompleteness issue by minimizing the L1 norm within the set of feasible solutions to phi alpha equals S. So be sure to notice how this method is very reminiscent. It's very similar to the aforementioned method of frames, which basically minimizes the L2 norm instead of the L1. They are the same otherwise. As I understand it, this basis pursuit method requires more sophistication than the method of frames, but it is still solvable once you consider its connections to convex linear programming. So the standard form of a constrained linear programming optimization problem is shown on the screen. And by making the appropriate substitutions, the original problem, which is minimizing the L1 norm of alpha, subject to S equals phi alpha, um, can be really simplified. So C in the formula would be a vector with all ones. X would be our coefficients vector alpha, and the matrix A could be substituted with the matrix phi of bases. So from here, using either the basis pursuit simplex or basis pursuit interior algorithms, the minimization could quickly be achieved. Because BP is based on the minimization of L1, it has the advantage that most of the solutions will be quite sparse. And additionally, because it is based in global optimization, it can provide stable answers even if the data is given with a significant noise level, in which case the approximate decomposition would be given by the expression below. Now in the next few slides, we'll cover the computation.